Physical properties of soils. We need to understand physical properties of soils in order to be able to understand mineral nutrition. Physical properties of soil. Soil is composed of mineral and organic parts. The mineral parts are very well defined. The organic parts are basically material that is being recycled back into the environment, which means it's in a lot of different stages. Start out with a plant leaf. The plant leaf falls off of the plant. It starts to get degraded back by microorganisms. It goes through many changes up to the point where it is actually totally absorbed. All of the organic parts are gone of it. We're going to talk about all of these. Physical properties of soils. We have particles. There are three major particles: sand, silt, and clay. By definition, sand has a size of 0.05 to 2 millimeters. The function of sand is to provide structure. It also provides large airspace in the soil. Silt is 0.002 to 0.05 millimeters. This works with water retention. It tends to hold water in. It also allows it to compact. These are smaller particles. Then we've got clay, which is less than 0.002 millimeters in size. We're going to find out this has a very large surface area. It's involved in what we call CEC. CEC is cation exchange capacity. Organic matter, which is another part of this, also is involved in cation exchange capacity. When we look at soils, concept, basically we've got three different particles plus organic matter. The soil particle, sand, it is between 0.074 and 4.75 millimeters. That's according to the Unified Soil Classification System. If you go to the International Organizations for Standards, we see it's a little bit off. It says it's a 1/16 of a millimeter. We're going back to the size-wise up to about 2 millimeters. If we go to the USDA says 0.05 to 2 millimeters. We're looking something that's in the 0.05 or slightly larger size up to 2 millimeters. Once you get 2 millimeters, it's really no longer a sand. It's more of a gravel. Sand, by definition, normally feels gritty to the touch. That doesn't mean all sand is gritty. The sands of an hourglass tend to flow very easily because they've got a little bit more polished edges. Even if you took the sands of an hourglass and you put it in your hand and you rubbed on it, you would feel that it feels gritty. Sand is normally made up of silica dioxide. It is basically weathered rock. It's mechanical weathering, which means if you've got rocks tumbling down a stream, as they bang into each other, they chip off little pieces, and this becomes sand. If you have a rock that gets water in it, then it freezes, it will come apart. That is part of mechanical weathering if it gets hit by a bolt of lightning. All of this is mechanical weathering of rock. It occurs over time. When we look at the particles, we talk about silt. Silt, we're looking at 0.0039 to 0.0625 millimeters. This is the Uden-Wentworth scale. The International Organization for Standards goes 0.002 to 0.0625, which again is a 1/16 of a millimeter. The USDA is 0.002 to 0.05 millimeters. We're still all in the same general area. Silt normally comes from quartz and feldspar that is broken up through mechanical weathering. Silt feels flowery to the touch. It doesn't quite have the large enough particles to be able to feel gritty, so it's kind of flowery. When we look at clay, according to sedimentologists, we're looking at 0.004 millimeters. If we talk to colloidal chemists, they're going to look at 0.001 millimeters. If we talk to geologists and soil scientists, we're going to look at 0.002 millimeters. And they're all around in the same area, 1, 2, or 4 microns in diameter. Clay particles feel plastic to the touch. We know this. You've got modeling clay that feels plastic or slippery to the touch. When it's moist, you can actually take it and you can stretch it and you can form it into things. That's how they make a lot of pottery. We're back to the chemical weathering of rock in this particular case, because you start to get chemicals that get inside. These chemicals cause the smaller pieces to break apart. This gives you a soil particle size according to the USDA. You can see the red numbers is the International Standards Organization. They've classified sands in this particular case to very distinctive categories. You've got your silt and your clay down at the bottom of it. The reason I put this in here is because of the last two columns, which gives you a concept of how many particles you get per gram. If you're looking at a very coarse, which is between 1 and 2 millimeters, you get 90 particles per gram. Your surface area of 1 gram, which means if you measure the surface area of those 90 particles, it comes out to about 11 square centimeters. If I round that up to 12, it would be 3 centimeters by 4 centimeters. 3 centimeters is a little bit over an inch. 4 centimeters is a little bit under 2 inches, which is a fairly good size if you start thinking about it. If you get down to the very fine sand, which is what you're going to basically call hourglass sand, it says you've got 722,000 particles per gram. This is going to give you a surface area of 227 centimeters. 227 centimeters square is approximately 15 centimeters on a side, which is going to be about 6 inches on a side. So now we're looking at a piece of paper that is 6 inches by 6 inches. That's what you would find in 1 gram of sand, which means that we're now starting to get a much larger surface area. If we look at silt, we're looking at about 5 3/4 million particles per gram, surface area 454 centimeters. The real kicker in there is clay, because once you get down to the clay size, you're looking at about 90 billion particles. You're looking at a surface area of 8 million square centimeters. 8 million square centimeters. If you take the square root of that, that comes out to 2,800 centimeters. You divide that by 100 centimeters in a meter, that means you are looking at something that is 28 meters by 28 meters in area. The surface area of a clay, therefore, is absolutely gigantic compared to some of these other models. When we are dealing with this, clay has this huge surface area, which is something that becomes important. When we're looking at soil particle sizes, this gives you a difference in sizes of a very coarse sand, a medium sand, a fine sand, and a very fine sand. All of these photographs were taken at the same magnification. You can see the very coarse sand looks like boulders compared to the very fine sand, which looks very gritty. All of these are different types of sands. When we look at clay, clay has a structure like this. This shows 2 different types of clays on the left-hand side. It's basically got silicon, it's got oxygen, hydroxyl units, and it may have magnesium on the inside. When we look at different types of clays, we find things like this. Kaolinite is what we call a 1-to-1 lattice clay. Montmorillonite would be a 2-to-1 lattice clay. It shows you montmorillonite on the right-hand side. The pyrophyllite is also going to be a 2-to-1 lattice clay. Basically, these become important because you can see that there's a lot of place for water to attach to it. When we think of clay, we often think of seeing something like this. This is where you have an area that gets flooded. The water erodes into it. As you get this water eroding into it, you have this material that is going to sediment out. The sand particles are very large. They fall out very quickly. Then you get the silt and the clay on top of it. The clay, if it's a montmorillonite type clay, will dry out. It will cause these little pieces to fold up like that. You go through, you step on it, something breaks it up, it forms smaller pieces, it gets mixed back together, but if it gets wet again, it will separate out again. All of these are physical properties of particles that are found in the soil. When we deal with soils, we also deal with something called soil texture. Soil texture goes back to physical properties. This is your texture triangle. You've got 3 parts in here. You've got percent clay, you've got percent silt, you've got percent sand. These are very easy to determine with simple processes that are used in a laboratory. As your percent sand goes up on the bottom, you can see the percent silt and the percent clay come down as well. The ideal, if we want to call it that, farm soil is actually what you're going to call a loam. A clay is a very heavy soil. It's not necessarily that good. In Florida, most everything you're going to find is going to be a sand or a loamy sand, maybe a sandy loam. Very rarely gets outside of that. We use this in order to be able to break apart the various types of soil that we have.